In this video, we're going to talk about two concepts. One is integrating mass into stoichiometry. The other idea is, what do we do when we have information about both reactants? How can we predict which one is going to control how much product gets produced? The concept is known as limiting reactant. First, let's tackle stoichiometry and mass. We've got a kind of a dilemma in that in real life we have to weigh things in grams, but in chemistry all the action really happens by the mole or by the individual atom, which are related to moles. And so only moles can be compared in these balanced chemical equations. We have to convert mass into moles before we can do any stoichiometry, before we can compare compound to compound or reactant to reactant or reactant to product. There's an old saying that chemistry teachers have used over the years that visualizes this canyon. I have grams of some substance over here. If I want to know something about grams of another substance that's in the reaction, I can't cross the Grand Canyon, the old saying goes, without using the mole bridge. In the middle of every calculation that starts out grams and ends up grams, I have to use a mole ratio in the middle. Here's an example of what I'm talking about. Imagine that I have this reaction. Water decomposes to H2 and O2, and the equation is balanced this way. Now, when I'm talking about 2H2O becomes 1O2, for example, that's not 2 grams of water to 1 gram of oxygen. That ratio won't work. Or 2 grams of hydrogen to 1 gram of oxygen. Those ratios don't work when you're talking about grams. They only work with moles. So if my question tells me that I have 18 grams of water, for example, and it asks me how many grams of oxygen got produced, I can't do that simply. I can't compare grams to grams like I compared moles to moles in previous problems. I'll have to convert to moles first. Here's an example. This question is asking, what's the minimum mass in grams of Fe2O3 needed to produce 86 grams of iron? Now, this is fairly easy to do. We can set these up like we have set up these stoichiometry problems in the past, but we just have to introduce molar mass at the beginning and the end of the calculation to convert, first of all, mass into moles, and then moles back into mass. Here's how it goes. My starting point, as always when I'm doing a factor label type problem, is I write down what I know. 86 grams of iron. That's my starting point. Where do I want to get to? Ultimately, I want to know, the question is asking, what is the minimum mass in grams of Fe2O3 that will be needed to produce the 86 grams of iron. I can't directly compare grams of iron to grams of iron 3 oxide. That's not possible. I first have to convert to moles. So I'll use the molar mass of iron to do that. 55.847 grams per mole is the molar mass of iron. You can look that up in the periodic table. Now, with grams canceled, I have moles of iron. And now I can do a mole ratio. This is the mole bridge that I was talking about in the little saying. So on the bottom I want iron, moles of iron, and on the top I want moles of Fe2O3. The ratio is 2 moles of iron for every 1 mole of Fe2O3. Well, that will cancel moles of iron, but it still doesn't give me my answer. I have Fe2O3 in the top, and that stays. That's good, but it's moles of Fe2O3. So I want to convert back to grams. Again, I'll use molar mass. For every 1 mole of Fe2O3, the mass is 159.691 grams. So with grams on top and moles on the bottom, moles now cancel, and I end up with units of grams of Fe2O3. Now I just do my calculation, and I'm going to do this calculation for you on the calculator to show you a common mistake that happens if people aren't thinking about order of operations. Now as I do this operation, I'm going to multiply across the top. So 86.0, just 86 to the calculator, times 1 times 1 times 159.691. I'll hit enter just to clear that operation. Now, if I divide by 55.847 and then hit times 2, here's what I'll get. 491.823 grams. To 3 sig figs, that'd be 492 grams. But that's actually not the right answer. Here's why. The calculator does this operation so that it divides the 137,733 by 55.847, and then after dividing, it multiplies that quotient by 2. That's not really what I want it to do. I want it to divide 13,733 by the product of 55.847 times 2. So I'm forced to do the operations in the correct order by doing this. First I'll go 86 times 159.691. I'll hit enter. Then, after I hit divide by, I'll open a set of parentheses. Then I do 55.847 times 2 and close my parentheses. Now it'll do the 55.847 times 2 first, and then it'll do the division afterwards. Hit my enter key, and now I get 123 grams, which is the correct answer. Here's another example. This is the same reaction, but the question is slightly different. Again, we're starting out with this knowledge. I want to produce 86.0 grams of iron. But what I want to know this time is how many grams of aluminum are going to be consumed. So my starting point is here, my ending point is over here. As always, I start out by writing down my starting point. I know 86.0 grams of iron is what I'm starting with, or what I want to end up with in the reaction. The answer that I'm trying to find is grams of aluminum. That's my ultimate goal here in my calculation. I can't go grams of iron to grams of aluminum. Can't cross the Grand Canyon without using the mole bridge. So I need to convert grams of iron into moles of iron. That takes the molar mass of iron, 55.847 grams per mole. With grams canceled away, I now have moles of iron, and I can use the mole bridge. So the mole ratio here is 2 moles of iron to 2 moles of aluminum, and that comes from the balanced chemical equation. Those numbers there, the 2 2's, they're just the coefficients on the species in the equation. With moles of iron now canceled, I have moles of aluminum. Part of that's good because I have aluminum in the answer, but part of it's not good because I don't want moles, I want grams. But I convert from moles to grams very easily by using molar mass. The molar mass of aluminum is 26.982 grams per mole, and with the mole on the bottom and it cancels, I end up with grams of aluminum. So then I just do my calculations. 2's actually cancel. So I just take 86 times 26.982, divide by 55.847. The answer to 3 significant figures is 41.6 grams of aluminum. You try one. Once again, our starting point is we know that we want to produce 86.0 grams of iron. This time we want to know how many grams of Al2O3 are produced at the same time. As always, start out by writing down what we know. The given information is 86.0 grams of iron. What do we want to find? Well, our target units are grams of Al2O3. That's where we're trying to get. This is grams. I can't do stoichiometry with grams, so I first use molar mass to change it to moles. So 55.847 grams per mole changes grams of iron to moles of iron. Now I'm on the mole bridge. 2 moles of iron react with 1 mole of Al2O3 because of the coefficients in the balanced chemical equation. At this point, I'm now dealing with moles of Al2O3, but I want grams of Al2O3, so I use molar mass. The molar mass of aluminum oxide is 101.961 grams for every mole. So by putting the moles in the bottom, grams on the top, moles are going to cancel, and I end up with units of grams of Al2O3. That's what I want. So I do my calculations. My answer should have 3 significant figures in it, and it's 78.5 grams. In most reactions,